Unveiling the complex world of atmospheric tar balls. Welcome to an in-depth exploration of atmospheric tar balls, a fascinating aspect of our planet's aerosol dynamics. In recent years, tar balls have emerged as a significant topic in atmospheric science due to their implications on air quality and climate systems. Today, we aim to unravel the formation, properties, and effects of these elusive particles. What are atmospheric tar balls? Atmospheric tar balls are carbonaceous particles, primarily spherical, originating from biomass and biofuel combustion. Unlike soot, which exhibits a structured geometry due to its graphitic layers, tar balls are amorphous, often comprising up to 90% carbon. Their distinct morphology and elemental composition set them apart from other carbon-based particles, adding another layer to our understanding of aerosol complexities. Formation of tar balls. Tar balls are generated primarily through gas-to-particle conversion processes in smoke plumes. During biomass burning, a plethora of low-volatility organic compounds are released. These compounds, upon cooling and aging of smoke plumes, condense and undergo polymerization, forming tar balls. The transition from gaseous to particulate phase in minutes to hours reveals the rapid atmospheric dynamics at play. This process distinguishes tar balls from other particulates like soot, often formed at higher combustion efficiencies. Properties and characteristics. The typical size of tar balls ranges from 30 to 500 nanometers, detectable through sophisticated equipment like transmission electron microscopy. Electron microscopy not only identifies their spherical nature but also reveals a homogeneous composition primarily of carbon and oxygen. Unlike typical aerosol particles that engage in hygroscopic growth, tar balls become largely insoluble post-formation due to radical-induced polymerization, maintaining a consistent size distribution even through atmospheric aging. Atmospheric behavior and mixing. Tar balls predominantly exhibit external mixing states, meaning they coexist with other particle types without fully combining. Unlike hygroscopic aerosols that easily interact with water vapor, the polymer structure of tar balls renders them resistant to such interactions unless significant conditions facilitate mixing. This resistance to internal mixing with hydrophilic substances like sulfates underscores the unique atmospheric behavior, enabling them to persist as distinct entities despite prolonged atmospheric residence. Occurrence and environmental impact. Tar ball prevalence is closely tied to biomass burning events. Regions undergoing seasonal agricultural burning often report elevated concentrations of these particles. For instance, field studies within the African savanna reveal significant tar ball occurrences in post-burn analyses. However, their abundance tends to decrease in aged plumes and regional hazes, as coagulation processes eventually integrate these particles into larger aggregates, diluting their apparent presence. Optical and climate effects. While tar balls may not be as optically absorbing as black carbon or soot, their potential to absorb sunlight cannot be dismissed. Their existence introduces complexities into the optical characteristics of plume clouds, as their slight absorption properties can influence the radiative forcing calculations critical to climate models. Furthermore, despite their insolubility, the eventual dissolution when coagulating with hydrated particles can potentially enhance light scattering and absorption, indirectly affecting atmospheric visibility and climate dynamics. In summary, atmospheric tar balls represent an intriguing particle type within the family of carbonaceous aerosols. As intermediaries transitioning from volatile organic gases to stable atmospheric particulates, they embody a critical phase in the life cycle of biomass smoke particles. Understanding their formation processes, properties, and atmospheric behaviors equips us with better insight into their role in aerosol cloud interactions and climate systems. The study of tar balls not only enhances our comprehension of aerosols but also highlights the intricate complexities underlying atmospheric sciences. Thank you for joining us in this expert-level exploration of atmospheric tar balls. We invite you to delve deeper into this and other topics by leaving your thoughts and questions in the comments section. If you found this analysis insightful, Please consider subscribing for more cutting-edge content on atmospheric sciences. In our next episode, we will explore the evolving dynamics of aerosol interactions with climate change. Until then, stay curious and informed.